Welcome to this presentation entitled Introduction to the Derivative of a Function at an arbitrary point x as a limit of the incremental quotient. By the end of this presentation, you are expected to understand and make sense of the chaos of symbols which we see on this page. And also, you must be able to decode the story told by this kind of a graph. And basically the story starts from the simplest case which each one of us is expected to know, which is the case of calculating the gradient of a straight line given on the system axis is given there. So if we're given 2 points, x, comma, f of x, where x is the value of the function at a given point x, and also we note that to move from this point x to the next point here, we need to experience the coverage of the space between the 2 points, which we label here as change in x. So change in the variable x or the increment of the variable x, so that this point here is this x plus the increment, which we denote this one. And then for that, we can evaluate the function and get another point on the straight line here, which is x plus delta x, comma, f of x, delta x. So this symbol is pronounced as delta. So then to get the gradient, we all know that we say m, the gradient, which is y2, which is this value here, which is f at x plus delta x minus f at x all over. If we now say x2 minus x1, we see the difference is going to be that. That is what we're going to write there. And this is what we call the incremental quotient. So we're saying here, we're going to introduce the derivative of a function as an incremental quotient. Actually, this is the incremental quotient, and for the line, we all know that this gradient will be given as a constant, a constant number. So, but in general, we're not talking about functions which you can plot on the system of axis. We need to have something similar to determine the gradient of a curve in general. In that case, we're talking about a situation of this nature. Let's say we've got a curve passing through the 2 points there, and then actually this line which you had there is now acting as a second line of the curve, cutting the curve at 2 points there, and the east gradient there is going to be understood as the average gradient between the 2 points, the average gradient of the curve of y is equal to f of x, and then that basically we can call it the gradient of a second line. So this is our initial second line we're going to have there. So the other line which we've got here, let's say we wanted to approximate it or determine the gradient or the slope of this curve at this point. The slope of this curve at this point will be represented by the slope of the tangent line at this curve, which we can present this way. So now the tangent line will be line which touches this curve at a single point here, the unique point here, and its gradient you are going to name m exclamation mark t. That's a unique line which passes through that point, that single point which shares with the curve. So the slope of the curve will be the slope of the tangent line. And with respect to the curve, the slope of this tangent line will be referred to as an instantaneous slope. The slope of the curve at this instant when x is at this position. So now to approximate that, we're going to follow a process in this way. Now we slide this point along the curve, in that way reducing the change in x, like what we have here. Our change in x runs from there to there, but if we slide this point, we'll find that the slope of this second will be reduced as follows. Now slide that point to there, you will see that this ms1, the slope is less than the slope of this second line there, and actually also the change in x has been reduced to this kind of a position. So we can continue with that in this way. We get to the next line, so I find that the second now passes through this point, and whose corresponding x on the horizontal here is closer to this x. The change of x has been reduced, and if we continue with that, we can get the third gradient of the second line, which we call him S3, which is actually the least compared to the starting point. This gradient is greater than that one, and the gradient is actually decreasing as the change in x is being reduced here. So if we continue that process, we can get a line like this, whereby now we can see the change in x is this small. Now if you consider this process now with delta x, the change in x approaching 0. Now we're introducing here a limiting process, and by saying delta x equals to 0, we must emphasize that now we're not saying that delta x is equal to 0. So delta x is a small change, but different from 0. So now if we look at this to the limit, we can see that when delta x is going to 0, now this gradient of the second line as delta is going to 0 will be approaching the gradient of the tangent line. That's what we have there. And that gradient of the tangent line would be taken as the gradient of the curve at that point, which we call the instantaneous rate of change. Because what we're having here, we're having fy is equal to f of x, which is written there. Now when we're getting this, we're actually having here what we can call the change in y. Like for example, if we're at this point here and that point there, and then here we'll have the value of f of x plus change in x, and there we're having the value f of x. Then this space here of the variable y, we'll call that change in the dependent variable y. So in other words, what we have here, we simply have got something here which we can call delta y over delta x. That now when we take this to the limit as delta x is going to 0, then it gives us something else. Let's see what it gives us. So in that case now, we're looking at this to the limit. So we're saying here, limit as delta x is approaching 0 of f at x, and we emphasize here that delta x is not equal to 0, so it can divide there. So in this case, we should notice that here, from what we said before, we said f at x plus delta x minus f at x. Remember, f is y, the y is equal to f of x. This we're going to call it change in the dependent variable y. So what we're doing here, we're simply calculating the limit as delta x is approaching 0 of delta y over delta x. Now, a limit, as we know, a limit may exist or it may not exist. In the case that this limit exists, this limit is going to be called the derivative of the function y with respect to x. That's what it's going to be called. And at that point, I would like to also emphasize something here, which we should know, that when you're given a function y is equal to f at x, we know that the y is the dependent variable. We've said that already in this presentation, and our x is our independent variable. In this case, what we're looking at here, we're looking at the limit of the change in the variable with respect to the change in dependent variable. Now, in this case here, we're looking at the rate of change of the dependent variable with respect to the independent variable, and we're looking at it to the limit, and that limit we're going to denote it this way, and they call it derivative of y with respect to x. So that will say derivative of y with respect to x. So in this case here, x is the independent variable. The other term which we're going to use, which is very important for this chapter, is that we're also going to refer to x as we see there as the argument of the function. In this case, as independent variable there, we're looking at x as the argument in its simplest form as an independent variable. But you must understand that the argument of any given function can be more than just an independent variable, because it can be another function in the case that we've got a composite function. Like for example, if we've got y is equal to sine of x, and then let's say this is f, and then we've got another function which you can say y is equal to e of x, which we can call here g of x. Now, if we were to compose the two functions, let's say we've got x, set x here, and a set y there, and another set z, and let's say this x is a domain of sine, it will get its values there, and we'll know that if we've got sine as a function there, it will give us values there which are between -1 and 1. And then if g now x from this one to that, and our g in this case is e of what it picks on there, and we'll end there. So the function, the composite function which is going to come up here is going to be an h, which is an h of x, because it takes values from x here, and then it's going to be a function which first of all picks x by means of sine. Then that value there, sine of x, will be picked by e. Then we end up with something like e to the power sine of x. So in that case here, the argument of e is the function sine, and the function sine, its argument is the independent variable x, and also as an independent variable, we can also look at it as a function. When you're looking at the function, says y is equal to f of x equals to x. So what I'm trying to emphasize here, that when I'm saying x here is the argument of the function f, you must understand that this argument x, the argument can take two levels. Initially as a simple independent variable. The second level is one as a function of some argument. But as long as we're writing this as dy dx, we simply mean that in the final analysis, never mind how many composition of functions we've got here, the function in the final analysis depends on x, so the derivative is going to be computed with respect to x. Exactly at that point, we'll see that in the actual calculations, when we compute derivatives using this incremental quotient, we're also going to come across expressions of this nature, whereby we'll be having a limit as delta x is approaching 0. Now, if we borrow the language which we've used here, just check that the position of y there has been taken by x. So if we borrow the same language whereby we're saying the derivative of y with respect to x, so here, using this same notation, we're going to use d here, dx, and then this now, we're going to call it derivative of x with respect to x. Now, in the language of the argument, basically we'll be saying here, derivative of the argument with respect to itself, because the argument is x in that case here. So that is what is very, very important there. So what you need to know here, that a derivative of a function at an n upright point is given as a limit of incremental quotient and is denoted this way. And also important, you can know that if we borrow that kind of language and use it here, if we get something like this, we can actually call it the derivative of the argument with respect to itself. That's going to be very, very important. Now, going forward, you will see that starting from the beginning, you can see that from here, with the function, we started with a straight line, we introduced a curve, then what followed was a tangent line at a given point like this one. So what we want to show you now is that process of calculating the derivative, which you said we're going to denote this way as dy dx, which is the limit as delta x is approaching 0 of the incremental quotient f of x plus delta x minus f of x over delta x. So this process, we said if limit exists, we're going to denote it this way and say dy dx, or derivative of y with respect to x. And in this at this stage now, I would like to show you that this actually results in another function. For example, at this same moment here, when we have this x, we have the gradient of this tangent line, its value corresponding to this x. So I can say the derivative of this function at this point x is equal to the value of this gradient. So there we're having simple a point which you can say x comma mt, that's a point. But this one is the value of the derivative. Now, to make sense of that, this actually gives us a function. We're going to take another point along this curve in this way. We've got that point now. We've got another point here with a tangent line, which also have got its own m. Let's call this one here. This one is mt there. Let's say this mt1. That's another one. So then, if we look at the value of the value of this slope at this point, we get another pair. So for each one of the points, as the point slides along the curve there, we're going to have a value of a gradient, which in that sense, that gives us a experience of what a function does exactly. At a given point, you are given a unique value. So that will happen again if we take another point there. For this tangent line, green here, we're going to have another gradient, and following that, we're going to have another gradient there, and there. Next, we can have another gradient of this tangent line passing there. So what the message is here is that simple, that the process of calculating the incremental quotient actually gives place to another function, which in this case, we're going to denote it as follows and say f prime x. So this function, which we're going to call derivative of f, is a function which for each given value of x, it assigns us the value which is equal to the slope of the tangent line at that point. And we must understand that the slope of the tangent line at this point is also considered to be the slope of the curve. Now, at this point, the curve and the tangent line share the same slope. So the slope of the curve is given by the slope of the tangent line. And that process, you can see, it gives you another function, which is a function of x. In other words, now, we're simply getting a pair here. Starting with the function f, we've got a second function, which you can call the first derivative of f. Why I'm saying the first derivative? Because this is a function of x, we can actually also compute its derivative, and then we'll then be coming to as what you can call the second derivative. And using this notation, we'll write here d2 there, y dx with a 2 there, meaning that we're calculating the second derivative. I hope you understand that at this stage now, I'm actually focusing on the notation. For example, this is the notation of the first derivative, which actually, the first derivative is a function of x which by right is a function for which we can calculate its derivative, and that will be the second derivative of the given function. Let's say y is equal to f of x. So already with taking the first derivative, we come up with a pair here, a function given and its derivative. And then at this point here, now we'll be giving a function given being the first derivative, and the second pair there will be the second derivative of that. So what will follow is actually to take particular functions and the different types of functions and do this kind of computation and see what kind of functions we get. And those functions we get, we're going to call them derivative of a function. For example, it could be a function like a monomial like x to the power 2. Would like to apply this and see what do we get what kind of a function do we get when we apply this limiting process to that using the incremental quotient. Very important at this presentation, we start by pointing out at that incremental quotient that if this incremental quotient, limit of the incremental quotient exists, it will give us a derivative, and the derivative is always a derivative of the function with respect to its independent variable. But you should understand also that the independent variable has got another name which you call an argument, and that argument we said can come in two levels, initially as a simple independent variable x or as another function. Even then, as a simple independent variable x, it can be taken as a function which is y is equal to f of x equals to x, which is actually what we call the identity function, a function which simply does nothing, takes x and it gives back x. Or at the second level, it can be that that function is not a function which is an identity function like this. Then you get an argument of function like here e, being another function like sine. In this case here, we'll say basically the function h is e, but e acts on another function sine, and then e here. In this course, we're going to refer to this e here or any other function in that same position as a leading function. That terminology we'll use it in our process of differentiation. At this point, I hope you have understood how we get the derivative, and that we can do the same process again to understand to get the second derivative, and also to understand that if these limits exist, very, very important, if these limits exist, this limit is going to be called the derivative of y with respect to x, and it's going to be denoted this way. And I said in our calculation, we're also going to experience or come across this kind of a limit, which was going to, if it exists also, we're going to denote it as dx, and this we're going to call it, because this is what we call the argument function, we're going to call it the derivative of the argument, and this limit we're going to call it the derivative function. Then we're going to see how these two interact when we compute the derivative. Is very, very important to note that and understand what these limits are called. This will be derivative of y with respect to x, and this will be derivative of x with respect to itself, or simple the derivative of the argument. So if all that notation and the type of computation you're going to do is clear, then at that point I'll say the basis for introducing derivatives of particular functions like polynomials, trigonometric functions, exponential functions has been set. Then let's meet in the next presentation to take each one of these type of functions one by one to understand the process of differentiation. At that point, I would like to say thank you for listening. My name is Charles Wasfanam Sibro.